James Webb Space Telescope is revolutionizing our understanding of the early universe. It is revealing those distant galaxies and the cosmic processes happening there to us in astonishing and complete detail. But with every new discovery, it is also presenting us with some controversies and very big questions, especially about a very important era of the universe. Reionization. Reionization is a very significant period in the timeline of our universe. Reionization is the time when the first stars and galaxies of our universe came together and completely changed the map of our entire cosmos. The universe was fundamentally transformed completely. Since the Big Bang, our universe was going through a dark age, but the stars and galaxies together ended that dark age of our cosmos. It is believed that this dark age ended about 1 billion years after the Big Bang. But the recent data from JWST has challenged this timeline. According to the latest observations from the James Webb Space Telescope, the era of reionization ended about 350 million years earlier than we had estimated. Because of this, questions are now being raised about the models we have created. Everything we have learned so far about the birth of this universe, are all those things just what we have assumed? Are the major theories that have been built on these models all wrong? In today's video, we'll break down the reionization period and explain how James Webb Space Telescope's discoveries are creating tension among cosmologists and how new theories can help us explain these surprising results we're getting from James Webb Space Telescope. Is it possible that all the models we've made about the early universe are missing a lot of important information? Or have we always been making a big mistake in defining this universe? Let's find out how James Webb Space Telescope can help us rewrite the rules of this universe. And what could this mean for the origin of our universe and for our human race? What is the Epoch of Reionization? The reionization period is one of the most important periods in the cosmic history of our universe. It started about 100 million years after the Big Bang, when the first stars and the first few galaxies began to form in the universe. Those stars had started emitting intense ultraviolet radiation. It was so powerful that it was enough to break hydrogen atoms. This radiation broke those early hydrogen atoms into protons and electrons, and this process of reionization gradually spread throughout the universe, turning our universe from a neutral state to an ionized condition. The universe, which used to be cold, had now become hot. Hydrogen is the most abundant element in our entire universe, so the changes that occurred in the universe during the reionization period were very profound, which was directly affecting about 75% of the matter present in it. During this period, the gas present between the galaxies that were forming had become completely transparent. Because of this, light got a chance to escape, and during this time, light was able to travel freely in the universe for the first time. These changes were very critical because the galaxies we see today were shaped by these very changes, and this determined that these structures in the universe could grow rapidly. That means during the reionization period, our universe started to take the shape that we are able to see today. This era of reionization ended when all the hydrogen present in our universe became fully ionized, and our astronomers believe that this phase lasted for about 1 billion years after the Big Bang. But recently, discoveries made by James Webb Space Telescope have revealed that the era of reionization ended much earlier than we previously thought. The era of reionization had already ended between 550 to 650 million years ago. And if this is true, then the early universes, our models need to be improved on a large scale, and this could also become a big problem for us. These new results are exciting for us, but they're nothing less than a puzzle. When our astronomers first studied the reionization period, they did it based on the cosmic microwave background, which is the afterglow of the Big Bang. And a lot of studies were also done based on the Lyman alpha forest, which is a pattern of hydrogen absorption lines. When these two methods were combined, we got an idea that the period of reionization lasted for about 1 billion years after the Big Bang. But when James Webb Space Telescope looked even deeper into the early universe, the surprise we got is something we are not able to place anywhere on our timeline. James Webb Space Telescope surprising findings. The James Webb Space Telescope has given astronomers the opportunity to look much deeper into the universe than ever before. We had never gone this far back in time before. James Webb Space Telescope has looked right into the middle of the Reionization era, and there we found some truly astonishing things. Much more than we had estimated, and much more. Extreme ultraviolet emitting galaxies were present there. These bright and energetic galaxies are so powerful that they alone could have ionized the entire universe. This challenges our belief that the process of ionization was a very long and slow process, and that it must have ended gradually over billions of years. This discovery tells us that the Reionization period must have ended hundreds of millions of years earlier than we had thought, because the presence of those very bright galaxies in the early universe indicates that those galaxies themselves must have ionized the universe. But now the problem here is that if the Reionization period ended so early, the cosmic microwave background and the Lyman alpha forest, both reliable cosmic indicators, should have appeared different to us compared to today. And this very difference is creating a major tension between JWST's observations and our models. Although scientists are working to find solutions for this, even then, if James Webb's observations turn out to be correct, the questions will be raised on the models we have created. What could be the reason for this? One possibility is that in our current models, we might have missed some very important processes, like recombination, where ionized protons and electrons combined again to form a neutral hydrogen atom. If recombination was happening much faster than we thought, then at that time, extra ultraviolet radiation would have been needed to keep the entire universe ionized, which we have seen in James Webb Space Telescope's findings, and James Webb Space Telescope can explain this very well. The second possibility is that the early galaxies forming in the early universe were evolving much faster than we thought. Because of this, they were releasing a large amount of ultraviolet radiation into the surrounding space. This means that whatever James Webb Space Telescope observed is an unexpected phase of cosmic evolution in our early universe. But until more data comes in, our scientists will continue to grapple with these astonishing discoveries. Because we don't have any tools available to verify James Webb Space Telescope's findings, because this is the first time that we are able to look so far back in time into the universe. So we hope that when we get more data from James Webb Space Telescope, we will be able to form a solid opinion about this. Resolving the mystery between James Webb Space Telescope's data and our previously established models. This difference tells us how little we actually know about the early universe. Despite the debates in the scientific community, they are due to this telescope's findings. For that, we need even more observations and better models that can help us understand how hydrogen recombined at that time and how galaxies evolved in the early universe. In the coming years, by combining the data we get from James Webb Space Telescope and future space missions, we will be able to clarify whether the results from James Webb are pointing towards new physics or if it's just James Webb Space Telescope itself. Astronomers, particularly from the European Space Agency, await data from the 2023 Euclid mission and upcoming surveys from the Rubin Observatory in Chile, so that scientists can get some answers to this missing puzzle from there. However, at the same time, astronomers are also re-examining our existing models to see if there might be any shortcomings in them. For example, how much radiation was needed to ionize hydrogen? Was it less or more than the value we predicted? Are we wrong here? Meanwhile, some scientists believe that recombination must have played an important role in this process, which we have ignored in our models. Meanwhile, some scientists also speculate that the formation of the first stars in the early universe happened. They were extremely large and very powerful, and because of them, the process of reionization became much faster. But one thing is certain, James Webb Space Telescope has opened a new chapter in our exploration of the universe, and the debate about reionization will continue for years to come. Julian Munoz and his colleagues are working on this cosmic mystery with the hope that when new data arrives, they will finally be able to uncover the true timeline of reionization and take a step forward in solving this cosmic mystery. The answers we get from future discoveries will not only reset our understanding of reionization but also our understanding of this universe. In fact, they will also further strengthen the foundation of our modern cosmology. This is a very exciting time for scientists. Every observation being made with the James Webb Space Telescope is bringing us even closer to the true nature of this universe. Now we are able to truly understand it. And seeing this, it seems that James Webb is proving to be completely successful in its mission. Conclusion: the results obtained from the James Webb Space Telescope have sparked a new scientific debate which could change our understanding of the evolution of our universe. If reionization ended earlier than what our previous models predicted, then it challenges all those models and ideas that we had built based on those models. Like how the first stars and galaxies were formed and how they advanced this universe. These discoveries show how little we know about the early universe and how much we still have to learn. As Julian Munoz explained, this is not just a matter of one or two galaxies changing, but a question of the evolution of the structure of the entire universe. What happened is true, but neither we nor our models ever predicted this, yet it happened within our current models. To resolve this tension, scientists need to work on even more detailed observations and new refined theories. With more missions like the Euclid mission and data coming from the Robinson Observatory, we can try to solve the mystery of reionization. But until then, the James Webb Space Telescope will continue to challenge our old ideas and open up new paths of discovery for us. This journey to uncover the mysteries of the universe has only just begun, but one thing is certain: we humans have never fully understood the universe. This is just the beginning of those astonishing discoveries. Friends, you might remember that in the previous episode, we talked about how James Webb Space Telescope is better than Hubble and how both telescopes work to capture this deep space image. Friends, this video is about the first colored image from James Webb and what conclusions we can draw by looking at this image. By the way, when you look at it, you won't see much difference between the images from Hubble and Webb. Both are almost the same, but if we go into detail, we can see quite a lot. So let's start today's video on this note. Friends, we already covered point number 1 in the first part, which was about the performance of telescopes. So now let's move on to point number 2. Areas of the sky that appear to be cosmic voids are not always empty after all. That means the parts of space that seem completely empty to us are actually not empty. By the way, we have known this theory for quite some time, that the parts of space which appear empty to us are actually not empty. But this first picture from James Webb gave us the proof we needed to confirm this theory. We have seen many such regions in space where neither stars nor galaxies are visible. Scientists were surprised to see such large voids and wondered how this could be possible, how such a huge part of space could be empty when our universe is supposed to be homogeneous. Now here scientists thought that maybe there could be some objects in these large voids that are quite small, faint, not very bright, and also have less mass. Or maybe those objects are very far away, which due to our technological limitations remain a big mystery for us. In such a case, it was thought that maybe all those objects could be hidden behind some cosmic dust, which our telescopes are not able to see. Or maybe it's something else. You can see in this image that the regions at the edges of the picture, at the top and bottom, and some parts in the middle appear completely empty. This image was taken by Hubble. Now, see this one from Webb. Those regions in Hubble's image where everything appeared empty. But in this image from Webb, we can see countless galaxies there. Yes, these regions are definitely sparse. That means not many objects are found here, but it's definitely not empty at all as was previously thought. James Webb not only found these objects, but also identified them separately and examined their properties. Meanwhile, Hubble wasn't even effective in observing these objects. This makes one thing clear: the more we look into space, the more we will definitely find something somewhere. Space is definitely not empty at all. Point number 3, the structure of the largest, most massive early galaxies will finally be visible to us, meaning now we will be able to see the biggest and heaviest early galaxies. When you look through Hubble's eyes, the farthest object you can see appears very blurry. That object looks just like a smudge in the picture. But if we look at this new image from Webb, we get to see a completely new view. In this picture, we can literally see the farthest galaxies, and even just by looking at them, we are also able to detect their structure. We can identify stars and galaxies separately by their structure, which is a big deal. Here, you must be able to easily detect both nearby objects and distant objects. The main galaxy cluster in this image, Southern Massive Cluster Survey 0723, is calculated to be 4.6 billion light years away, but you can easily see the objects redshifting in this image. Now, what is redshift? Let's take a quick look at that first. When light comes from a very far distance and reaches us after covering a long distance, the energy of that light particle, that is the photon, keeps decreasing during this journey, and on the opposite side, its wavelength keeps increasing, or you can say that the wavelength gets stretched. Now look at this spectrum and notice that as we move towards the red color, the value of the wavelength on the spectrum keeps increasing. And the opposite is also true. As the wavelength increases, we will see it as red color on the spectrum. You must have noticed that we often compare redshift with the Doppler effect. And for physical significance, the example of an ambulance is given as the ambulance, or let's say the magistrate, comes closer to us, the sound of its siren increases, and as soon as it passes by us, the sound of its siren starts to decrease. This is a perfect example of the Doppler effect, but this Doppler effect The picture at this point is confirming one more thing, that space is actually expanding, which is proof. Sir Edwin Hubble's observation and the Big Bang theory as well. Hubble, slow, it says that the more redshifted the light coming from any object is, the farther that object will be from us, and the faster that object will be moving away from us. That means the space between us and that object is expanding just as quickly. So if you look closely at this picture, you'll find several points here that are highly redshifted, which means, according to Hubble's law, this galaxy is the farthest away and is moving away from us very rapidly because the space between this galaxy and us is expanding very quickly. So from here, this picture also proves the expanding universe and Hubble's law. We know that accretion and mergers, these two factors decide how a galaxy will evolve over time. In astrophysics, accretion means the accumulation of particles into a massive object. That is, small particles coming together to form a larger object which then gravitationally attracts even more matter. An accretion disk mostly contains gases, and almost all astronomical objects like stars, planets, and galaxies are also formed through this accretion process. It had only been a few thousand years since the Big Bang. The universe had now reached the point where it had cooled down enough for atoms to form. Now atoms had formed, but because of the heat, the atoms still had a lot of kinetic energy, so they couldn't stay in one place. But as the universe expanded and cooled further, the atoms also lost their kinetic energy. It's believed the first proto-galaxy formed by combining with dark matter. As accretion kept happening, galaxies kept forming, and the accretion that happened inside the galaxies led to the formation of stars. However, we only have indirect evidence for this theory. Their birth happened in this way, but their evolution started with mergers. In this image, the more redshift we see, it's possible that we might see early galaxies there, or we might see these galaxies evolving. We know that the galaxies which are in a galactic group or clusters evolve differently in terms of shape compared to galaxies that are alone. That means the evolution of isolated galaxies and groups of galaxies happens in different ways. If we want to track the evolution of galaxies, then this Webb image and many such upcoming deep field Webb images will help us observe the evolution of these galaxies. But how? So we have to remember here that now we have 270 times more resolution, which directly means that there is an increment of 700 in the number of pixels. That means the galaxy which appeared as 3 by 3 pixels in the Hubble image will now appear as 8 by 8 pixels through the eyes of James Webb Space Telescope. This lets us observe galaxy shapes and configurations over cosmic time and by location. And with the help of these images, we will be able to see our universe growing up throughout its history. But do you know that some galaxies are imposters and they become a big problem for us? But we will learn about them in the next part of this video. But if you haven't watched the first part of this video, do watch it. You will find the link in the description. Friends, we are trying to understand this image in great detail. Today, we have talked about 2 points. In the upcoming videos, we will cover more points, and we are also going to cover all the images from James Webb. Countless mysteries are buried in the infinite depths of this endless universe, and our human civilization has been trying to understand this universe for so many years. In the era of modern technology, this work is done by these telescopes floating in space, whether it's discovering new galaxies, whether it's searching for planets like Earth, looking for life, or uncovering the mysteries of space and peering into the past of this infinite universe. All these tasks are made possible by space telescopes, and in this long list, we humans have also launched such a telescope, which has completely changed all our ideas about the universe and proved our concepts wrong. It has brought the very first moments of the Big Bang right before our eyes. The launch date of this mission was postponed several times, its budget was cut, and every time the mission got delayed. As a result, its cost rose to $10 billion. That means, in the history of humanity, this was going to be the most expensive telescope ever. But finally, on the morning of December 25, 2021, the land of French Guiana literally trembled when the Ariane 5 rocket was launched, and with this tremendous roar, the James Webb Space Telescope had set out on its journey into space. At the L2 Lagrange point, about 1.5 million kilometers away from Earth, where it had to carry out its upcoming operations. Although it took this telescope an extra 5 months to start working after reaching there, the wait was worth it. In these more than 2 years, James Webb Space Telescope has completely changed our view of the universe. And today we will talk about 10 such discoveries of the James Webb Space Telescope and find out what exactly this telescope has discovered in this vast dark space. Number 10. Early Universe and Massive Bright Galaxies, James Webb Space. Before the telescope, astronomers believed that galaxies began with a small cloud of gas, dust, and a few stars, which gradually grew into an island universe as we see it today. But the ability of this telescope to see infrared radiation has given us the power to look even further back in space and time. When those galaxies were forming, they were observed by JWST. Some galaxies were from just 500 million years after the Big Bang. That means we were able to see the childhood of those galaxies, and unexpectedly, those galaxies were very bright. Studies found that those galaxies were much more than what we had predicted. They formed stars excellently. That means those early galaxies were star factories producing stars at a higher rate. Scientists had never thought of this, and those stars were also much more massive than astronomers had predicted. Apart from this, scientists also noticed some advanced structures in those early galaxies which were found in spiral galaxies. This was observed when the universe was about 2 to 3 billion years old, and at that time, stars were forming at the fastest rate. Here, the James Webb Space Telescope cleared up many of our misconceptions and gave us a clear idea of how galaxies evolved in the beginning. Number 9. Early supermassive black holes. We all know that black holes grow by swallowing clouds, gas, and dust when they pass near a star or a dust cloud. But when James Webb Space Telescope looked into the early universe, scientists were surprised to see supermassive black holes there. Because in the early universe, there wasn't enough time for a star to first become a black hole and then for that black hole to grow. Supermassive black holes could form, and James Webb Space Telescope saw more than one. There were many supermassive black holes there whose mass was more than 1 billion solar masses, and they formed just 800 million years after the Big Bang. This was truly a shocking revelation. After all, what was happening in the early universe that caused such massive black holes to exist right from the beginning? What's important here is that the James Webb Space Telescope not only observed extremely large supermassive black holes, but also very small supermassive black holes, which were about as massive as 1 million solar masses. Information about them was also discovered. And these smaller black holes existed in the universe even before this. This has given scientists an idea about the early evolution of the universe, and the data received from this telescope has challenged our concept of this universe. We have seen something that we never even imagined. Looking back in time, its power has made us and our science even stronger. Number 8. In the early universe, dust is found almost everywhere around us, from the dust under the mattress on your bed to the Milky Way, the dark clouds blocking our view at the center, and the dust seen in the spectrum of distant galaxies. It's everywhere. Even in our early universe, this same dust was dominating. The dust present at that time was made of carbon, which means that this dust came into existence in the universe much later. Because carbon is formed inside stars, and it starts forming inside stars much later than hydrogen and helium. Even after this, the James Webb Space Telescope has just after the Big Bang. It discovered this dust in a galaxy 1 billion years later. This dust had a unique chemical fingerprint which showed that it was made of particles of graphite and diamond, which likely formed in the first stars. In this way, James Webb Space Telescope has also clarified our vision about the earliest stars and dust. This has further advanced our understanding of dust, production, and galaxy formation. The cosmos is within us. We are made of star stuff. Carl Sagan said this, but James Webb has set out to find the origin of that star stuff. If we look at astronomy, some numbers are very important. It is moving away from this field, meaning it is expanding. But when Cepheid variable stars and type Ia supernovae were studied using the Hubble Space Telescope and other instruments, they gave a different value for the Hubble constant. A value of about 73 kilometers per second per megaparsec was found. The difference between these two values is what we call the Hubble tension. The James Webb Space Telescope has advanced this field for scientists. JWST has calculated the higher value of the Hubble constant with even more precision. But it still remains to be discovered why we are getting these two values. Two values for the same thing indicate that we still haven't understood the universe. Even today, we are still missing something in understanding how this universe actually works. Is there something wrong with our measurements or with the method? If that's the case, then figuring out which method is correct and which value is right is also difficult. For now, James Webb has shown us a direction, and hopefully we will be able to solve this mystery soon. Number 6. How stars are formed. We know that stars are formed from dense clouds of gas and dust, but unfortunately, dust blocks visible light and we haven't been able to observe that process until now. But James Webb Space Telescope can detect the infrared radiation coming through those dust clouds. As a result, star formation will no longer be a mystery. Now we will be able to observe that process through the telescope. For example, James Webb Space Telescope observed thousands of stars forming in the Eagle Nebula, which Hubble Space Telescope could not do. In addition, James Webb Space Telescope has studied the Rho Ophiuchi complex in great detail. From its data, we have observed dozens of new low-mass stars there. Some stars that are emitting jets are also lighting up the surrounding molecular hydrogen clouds. We also found this out from James Webb Space Telescope's data. That means now, no secrets can remain hidden behind dust clouds in the universe, which is a big achievement for us. This telescope has opened a new dimension of research for scientists. About 340 years ago, the light from an exploding star, the remnant of a fuzzy supernova, reached our Earth, and even today we can still see the remnants of that supernova. Today we know it as Cassiopeia A, which is spread out in the form of a shell about 10 light-years wide. Cassiopeia A. James Webb Space Telescope has presented the beauty of this stunning supernova to us through the infrared light coming from the supernova's gas and its hot dust. But this time, scientists were a bit surprised because the structure of the dust we found from that supernova appeared as the building blocks of planets and life. This proved that the heavy elements ejected by supernovas are what primarily make up cosmic dust. However, earlier studies couldn't prove how the amount of ejected material found in early galaxies actually got there. Now, scientists have hopes from the James Webb Space Telescope that by studying Cassiopeia A and other supernovae, we can understand how these supernovae were created and how they contributed to the formation of galaxies. We will understand how the dynamics work. Number 4. Within Jupiter, massive binary objects and ionized nebulae. About 40 planet-sized binary companions have been discovered in its depths, which are called jumbos. That means Jupiter, massive binary objects, and these bodies are defying almost every expectation. Scientists previously believed that binaries could only be possible in stars, but they never thought this could happen with planetary mass objects. No star formation theory supports creating such small objects. And if we assume that these objects are not like stars, but rather like planets, if they are formed in the circumstellar disk, then they cannot achieve a stable orbit, because one or the other object falls victim to a forceful ejection. So then, how did these jumbos come into existence after all? And what is their mystery? Do scientists now need to change their ideas and concepts about the formation of stars and planets? Do we now need a new theory about planet formation? Well, this is still a subject of research, but one thing is certain, the data from the James Webb Space Telescope is forcing scientists to rethink every time, and it's also helping us refine our science. 3 molecular exoplanets. James Webb's images have made a lot of headlines, but in exploration, James Webb's spectroscopy has played a very big role helping scientists detect distant galaxies undergoing redshift. Obviously, this also allowed us to estimate the distance, and besides that, we were able to determine the chemical composition of celestial bodies through spectroscopy. This is the best method for studying exoplanet atmospheres as it lets us examine them in detail. What are the conditions there? What is the chemical composition of the atmosphere? And are there any traces of life? All these things can be found out from James Webb Space Telescope's data, which shows the capabilities of our James Webb Space Telescope. For example, James Webb Space Telescope discovered methane, carbon dioxide, and methyl sulfide on the exoplanet K2-18b. The data showed it's a rocky planet in its star's habitable zone. This greatly increases the possibility of water being present there in liquid form. And in this way, the James Webb Space Telescope can also help us in the search for life in this universe. Number 2. Ring Nebula Mystery. Messier 57, that is, the Ring Nebula present in the Lyra constellation, is the most beautiful nebula visible in the sky. The Ring Nebula is a planetary nebula which is the final stage of stars like our Sun. Before James Webb Space Telescope, we only knew about the Ring Nebula, but James Webb Space Telescope has made the rings of this nebula even more mysterious. Before James Webb Space Telescope, we only knew about the Ring Nebula, but James Webb Space Telescope has made the nebula mysterious. Having such an observatory is a matter of pride for all of us. When a star is formed, a disk of a lot of dust and gas forms around it, that is, in its surroundings. This is what we call a protoplanetary disk, because later on, planets are formed from this very disk. James Webb has not only studied these protoplanetary disks with unprecedented detail, but has also presented some evidence of life there to us, James Webb. When the Space Telescope studied the formation of a nearby star, it found that there are 3 belts formed around the star. These have formed because of the dust present there. This shows that planets have formed in this disk. Additionally, the young star D200-3506 in the Orion Nebula has a protoplanetary disk. Here, James Webb discovered methylcation. It's a molecule that plays an important role in interstellar organic chemistry and the origin of life. Because of this, the James Webb Space Telescope is like a gateway for us from where we can reach any corner of this universe. We can observe the processes happening behind the mysterious dust and uncover the secrets of this mysterious universe. In the coming time, the James Webb Space Telescope may change many more of our concepts for which we need to be prepared. Friends, what do you have to say about the capabilities of James Webb? Please be sure to share your opinion in our comment section. Now, what are these imposter galaxies or masquerading galaxies? Your first question is probably this. Go ahead, let's search for the answers to all these questions and uncover the deep mysteries hidden in this picture. So Mr. GNJ11, this galaxy was the farthest one from us, located about 32 billion light years away from us. This galaxy was discovered in 2015 and it is believed that it came into existence 400 million years after the Big Bang. But in April 2022, scientists discovered another galaxy, which was a much more redshifted galaxy. It was named High Definition 1. This galaxy is considered one of the most distant galaxies ever discovered in the observable universe. It is located 33.4 billion light years away from us, and it is estimated that it came into existence just 330 million years after the Big Bang. So, the title of the most distant and oldest galaxy goes to the High Definition 1 galaxy. But the big thing is that it has not been spectroscopically confirmed yet. Yes, it's true that High Definition 1 appears completely red in color, and there is no short wavelength in this light. The wavelength of the light coming from High Definition 1 has been completely stretched. If we pay attention to High Definition 1's redshift, its redshift is 13.27. This means that the light emitted from High Definition 1 has traveled through space for 13.27 billion years to reach us. But when the light coming from High Definition 1 was split and its spectrum was observed, only one absorption line was seen in that spectrum, from which we couldn't determine anything. But if we had seen multiple lines in its spectrum, we could have determined how much redshift occurred in the light due to the expansion of the universe. So here we can say that we didn't have any tool for legitimate spectroscopy until now, with which we could find out how far an object is and whether it is actually a galaxy or not. Just like High Definition 1, there's another candidate for the farthest object named High Definition 2, but the problem is that it doesn't have any spectral lines at all. Now, it's possible that the objects we consider to be the farthest galaxies might not actually be galaxies at all. They could either be black holes or extremely bright stars. Besides that, they might be quasars or pulsars, and these are called imposter galaxies, which look like galaxies to us, but in reality, they are not galaxies. Now, no matter which telescope the image is from, just by looking at any red dot, you can't say for sure that it's a galaxy. It could be any bright object which Hubble was not able to fully differentiate. Now, the James Webb Space Telescope can closely study every entity visible in this image. Any red-shifted point seen in the background of this image could be a galaxy or even an imposter galaxy. But by studying the spectral lines coming from those objects in detail, this telescope will be able to determine whether the object is really a galaxy or something else. As we know, the James Webb Space Telescope is highly sensitive to wavelengths beyond 2000 nanometers. Any galaxy that is highly redshifted, like our record holder galaxy, can be studied in the same way. by analyzing the spectrum of every point, every object present in this image. We can assume that we don't accept any extraordinary claim until there is solid evidence in its favor. We are now in the era of the James Webb Space Telescope, the age of James Webb. Now we have so much capability that we can pinpoint any galaxy, and the evidence we need will be available to us through James Webb Space Telescope without any difficulty. Now this is not a big deal anymore. Now every new image from James Webb will set a new record. Now is not the time to create new assumptions in the absence of evidence. Rather, now is the time when we can see the truth and reality without any doubt. Thanks to James Webb Space Telescope, that now we are capable of replacing we believe with we know, and all this will only be possible with the help of James Webb. So let's first find out what exactly gravitational lensing is. When we see gravity at an extreme level, gravity creates some really fascinating visual effects. Einstein's general theory of relativity tells us how a massive body distorts space and time around it. When light passes near that massive body, the distortion of space causes the light to bend as well. It's similar to how light passes through a convex lens. A gravitational lens is formed when a large amount of matter is concentrated in one place. For example, when light coming from behind galaxy clusters passes near them, the distortion of space bends the light in such a way that it magnifies the stars and galaxies that are located behind the galaxy cluster. This effect is exactly like what we see when we look through a magnifying glass. This effect brings out the details of those galaxies that are extremely far away, and in this way, scientists are trying to study our universe using this gravitational lensing. Now let's look at this image from James Webb Space Telescope focus in the center where there is a galaxy cluster. That same galaxy cluster is responsible for gravitational lensing in this image. This collection of galaxies and dark matter acts as a cosmic telescope for us, allowing us to see magnified and contorted images of individual galaxies. Sometimes we even get to see mirror images of the same galaxy. You can see an example of this in the same image. On the left and right of the center, you can see some lensed galaxies in the orange arc. Here, the same individual galaxy is appearing twice in the arc. Look at this. The shape of this galaxy has also become elongated just because of gravitational lensing. Here, you can clearly see that the central part of the image is more affected by gravitational lensing, which doesn't even look right to us. Otherwise, this part is also filled with scientific data. Not all galaxies have been mirrored in this gravitational field. Only a few galaxies are showing us this mirroring effect. Apart from this, some galaxies appear to be stretching and some galaxies seem to be interacting with each other. Here we can clearly see how Webb has refined a detail in this image. In this image, we will also find some galaxies that appear completely red, which are among the oldest galaxies discovered by us. This image will take us even closer to the Big Bang, and gravitational lensing will help us see the upcoming images in even more detail. Friends, I hope today's 2 points are clear to you. If you still have any doubts, be sure to leave your doubt in the comment section. Also friends, you can watch the previous videos of this series by going to the link given in the description below. Otherwise, on the left side, you have a playlist given. By clicking on it, you can watch all the videos. Make sure to subscribe to the channel for the next video, friends. See you again with another new informative video like this. Till then, stay curious, be happy. Namaskar.